Now that we know about the shape of these molecules that we've been studying, we need to add on to it one more time, and we need to talk about polarity. Okay, what is polarity? It's where you have a different charge on one side than the other side, okay, at the poles. Okay. So we need to talk about dipole moments. A dipole moment is the direction of the polar bond in a molecule. And we use arrows to represent this. Okay, so we draw our little arrow like this. So it looks like a plus sign with one of the arms of the plus sign turning into an arrow. And the reason why we draw it like that is because that lets you know this is the side that's a little bit positive and this side is a little bit negative. Okay? Because it's pointing towards the more electronegative atom. So what does electronegative atom mean? What is electronegativity? Electronegativity is the tendency of an atom to attract shared electrons. So what does that mean? Well, that means that if you're more electronegative, you're going to attract the electrons to you more strongly than another atom that has less electronegativity. Basically, not all atoms share equally, right? So we've been drawing these bonds to show how atoms are being shared so that all of the atoms in a molecule can have an octet, can have those 8 valence electrons. But not all these atoms are going to share equally. Some are a little selfish, and they tend to hold the electrons a little bit closer to themselves. When they do, they're a little bit more negative because they have that negative charge towards them a little bit more. The other side, the one that is getting the electrons taken away from it, becomes a little bit more positive because those negative electrons are pulled away more often. Okay, and there's a pattern that we can see on our periodic table, just like some of the previous patterns we studied. So we can use our periodic table to help us determine how this electronegativity is going to work. Okay, so from left to right across the periodic table, your electronegativity increases. So as you go across, the elements over here tend to pull the electrons towards them when they're in a bond more so than these ones. Okay? And the reason why that is because as you go from left to right, you are increasing the number of protons in that atom. And protons are positive and opposites attract. So since these guys have more positives, they attract those negatives more strongly. Okay? So that's your left to right pattern. Then, as you go from the bottom to the top, electronegativity increases. Now, with what I just said about protons, that seems a little counterintuitive. The reason why electronegativity increases as you move up is due to the overall size of these atoms. Okay, so remember, these guys are smaller. They have less energy levels, right? Like we learned about those before. Like this row 1 only has a 1s energy level. That's it. Row 2 has 1s and 2s and 2p and so forth. So that means that the electrons that these atoms have are closer to the nucleus because they have less energy levels. So they're actually closer to the nucleus. So they're closer to that positive charge. And so they pull in a little bit tighter versus the ones down here where they have lots of energy levels. So those valence electrons are much further away from the nucleus. They're further away from that positive charge. So the pull isn't as strong because they're not as close. Okay, so that's why you see that trend. So as you go across in the diagonal, you have very weak electronegativity over here. So these ones do not hold their electrons very tightly. They get pulled away easily. While as you move over here, we have the really strong electronegativity. So these ones pull those electrons towards them. Okay? So that is your overall pattern. So use your periodic table to help you determine what these charges are going to be. Okay, so when we determine the polarity of a molecule, what do we need to look at? We need to look at those dipole moments. So that's based on that electronegativity pattern we just talked about. And we need to look at the overall shape. Okay, so those are the two things we're going to look at. So we can have non-polar molecules. That means that there is not an overall charge because the dipole moments are symmetrical, so it's even all the way around, and they cancel each other out. So here's an example. We have BF3 here. We have it drawn in its geometric shape. Now we need to use our periodic table, and we need to compare boron and fluorine. And between those two, we need to say which one is more electronegative. So find boron on your periodic table, find fluorine. Now thinking about that pattern we just talked about where it increases as you go from left to right, which one's more electronegative? The fluorine is. So we're going to draw our little arrows here where we have the positive side of the arrow towards boron and then the negative arrow pointing out to the fluorines. Okay, so what happens here is that every single one of these fluorines is a little bit negative. So all the way around you have negatives. They're all equal. All the way around the outside is equal. So they cancel out. So you have no net charge. So these are non-polar. Okay. On the flip side, you have polar molecules. These dipole moments are asymmetrical, so they don't cancel out. So on one side you have a positive while on the other you have a negative. Okay, so if we look here, this is water, H2O. So we need to look at our periodic table, look at the location of H, look at the location of O, and see which one is more electronegative. Okay, left to right, electronegativity increases. So we're going to point that arrow towards the O. Oops, sorry. There we go. Point that arrow towards the O. So we've got the positive towards the hydrogens, the negative towards the oxygen. So we have positives on this side of the molecule, we have negative on this side of the molecule. That creates a net dipole moment where one side is a little bit positive, one side's a little bit negative, so that is polar because it has two opposites. Okay, so therefore, polar molecules have an asymmetrical shape, and that usually means there's some lone pairs there, right, pushing to make that asymmetrical shape. Or they may have asymmetrical atoms, like this example. So this is not an asymmetrical shape, but the atoms are asymmetrical. So here we have carbon in the center, we have a hydrogen up here, and we have chlorines down here. So first, let's take a look at our periodic table, and let's look at the electronegativity comparing carbon and chlorine. Which one's more electronegative? So which way do we need to draw the arrow? And then also compare carbon and hydrogen, because that's going to have a different one. We've got to check that one too to draw our arrow. Okay, so carbon is more electronegative than hydrogen, so we draw our arrow pointing towards the carbon. So hydrogen becomes a little bit positive, carbon's a little bit negative. But now, compared to the chlorine. Okay, the chlorines are more electronegative than the carbon. Okay, so we draw the arrow going out this way. So we see up here, we have positive near the hydrogen and a lot of negative down here with the chlorines. So that is creating a polar molecule due to the asymmetrical atoms. So based on this information, you should now be able to look at a molecule and be able to determine whether it is polar or nonpolar.